welcome to the 30th lecture in this series. So last time I had introduced the notion of a vector field on a manifold. Now let's discuss some, explore some examples. So on Rn as regarded as a manifold, we know that we have a frame namely del by del x1 at a point P, del by del xn at P. So the partial derivative operators, actually let me not mention the P at just this. The partial derivative operators give a frame. So in other words, a basis for the tangent space at each point. And every vector field, any vector field in Rn can be written as x equals sigma ai del by del xi, where the ai functions are real valued functions on Rn are smooth. So in other words, i.e. a vector field on Rn is prescribed by n functions ai. So this is the same as saying equivalently vector field on Rn corresponds to a map from Rn to Rn, to a smooth map from Rn to Rn, because the smooth map is P going to A1 at P, An at P. Now this way of thinking about a vector field as a map of from Rn to Rn is useful when one talks about the integral curves, which I will discuss next when we come to ordinary differential equations and integral curves in the context of Rn. Then this viewpoint is helpful. All right, so this is in Rn. Now on the, let's move to the most general case, namely any smooth manifold on, let M be any smooth manifold P a point in M, V a vector, tangent vector at P. So then I claim that there exists a vector field there exists a vector field X on M with XP equals V. So another way of saying it is any tangent vector can be extended to a vector field on the whole of M, and this is immediately seen by looking at a chart around P. To see this, let U phi be a chart around P. We can write as usual, we get a frame, namely the coordinate vector fields give rise to a frame on U. So therefore we can write V equals some constants Ci del by del xi at the point P, where the Ci, Rn are just real numbers. Define. So at least locally, so this is my U, this is the point, and I have a vector V. At least on U, I can define a vector field which extends V in a very trivial way. Define Y to be a vector field on U by, well, I just take Y at any point Q I define it to be, I use the same formula as I have here, except that of course instead of del by del xi at P, I will be putting del by del xi at Q, but the Ci will be the same. So Ci del by del xi at Q for all Q and U. So clearly I've already written Y is a vector field on U, which according to our definition already means I'm assuming that Y is smooth, but in fact it's quite clear that Y is smooth simply because these functions are constant functions. We have seen that smoothness is equivalent to this, the coefficient functions being smooth, but here they are actually constant. Right. Now Y is still defined only on U, and but the good thing about Y is that Y at P is just Ci del by del xi at P, which is by definition V. So at least we have been able to extend the vector tangent vector V to a vector field Y only on U though. So if I want it on the whole manifold, I just do the usual trick of multiplying by with a cutoff function. Let phi be a C infinity function on M with support in U and identically equal to 1 in a neighborhood of P. Define the, as usual, whenever we want to extend something from a coordinate chart or from an open set to the whole manifold, we multiply the locally defined quantity, in this case Y, with the cutoff function and define the vector field to be 0 outside U. Define X Q equal to 0 if Q is belongs to M minus U, and define it xq to be phi q times yq if q is in U. And the fact that phi has support in U will ensure that this x is smooth everywhere. It is easy to check. X is smooth on M with this definition. It's certainly smooth on U, and it's smooth on M minus U closure. The only issue, as usual, is in the boundary of U. And so there it continues to be 0, and in fact it will be 0 in a neighborhood of the boundary, and one can argue that it's smooth everywhere. It's easy to check that X is smooth on M. So this standard way of extension will work here. All right. And since phi is identically 1 in a neighborhood of P, well, all I need is in fact that phi at the point P is 1. The neighborhood is also not necessary. So phi of P is 1 will guarantee that X at the point P is the same as Y at the point P, which is same as V, since that's what we had here. So any vector can be extended to bear a smooth vector field on M. And in fact, the same sort of idea will show that similar argument shows that this similar argument shows that the set of vector fields on M is not finite dimensional. And right, so here what one does is, again, one can start with, for instance, it's quite straightforward to see this. You start with a chart and take one, say, del by del x1, which is a vector field on the chart. One can multiply del by del x1 by various functions defined on U. For example, one can multiply by powers of x1 and then extend it to all of M. For example, it's enough to show that it's not finite dimensional. We can exhibit a linearly independent, infinite number of linearly independent vectors that will do the job. So here I can just take x1 times del by del x1, x1 squared times del by del x1. Everywhere I have to multiply by this phi, etc. This multiplying by phi will give a vector field on all of M. And since phi is identically 1 in a neighborhood of P, in a small neighborhood, in that neighborhood, I just get these vector fields x1 del by del x1, x1 squared del by del x1, etc. Of course, here as usual, when I say x1, what I mean is x1 is a coordinate vector on U, not on on u1. x1 is defined here, just the first projection. And if I want something on u, as usual, I'll have to compose with phi. In other words, look at the first coordinate function of, so this phi should not be confused with the chart map. So let me call the chart as something else. I've already used phi for the cutoff function. So let's call that alpha. So when I say x1, what I mean is alpha 1, the first component of alpha, etc. And this del by del x1, we know what it means. It is the del by del x1 here, which has been transported back to the manifold by the derivative of alpha inverse. Right. So for example, this set is linearly independent. Now let me give an interesting vector field on R2, not on R2, in fact on S1, on the circle. On S1, the one-dimensional manifold S1, which we regard as a subset of R2 as usual. Let x, the vector field x at the point x comma y, I define it to be y times del by del x minus x times del by del y. So now there are so I want to claim that this x is a vector field on S1. So there are two things to check. First of all, this what I have defined here is certainly a tangent vector to R2, but is it actually a tangent vector to S1? That is one thing. Second thing is, as usual, is it smooth as a vector field on S1? It's again, it's smooth as a vector field on R2. This right hand side is a well defined vector field on R2 and it's smooth there, but is so is it smooth on S1? Now first let's check that this is indeed, so first point is x at xy should belong to the tangent space at the point xy to S1. Now we know that we have seen that if we regard TP_S1 as a subspace of TP_R2, and which we identify with R2, this what I have written here will give rise to a subspace of R2 for every P in S1. So as the point P changes, I get different subspaces of R2. So if we think of TP_S1 as a subspace of R2, then TP_S1 is this subspace. We have already seen this when we talked about regular values. TP_S1 is all V in R2 such that inner product of V and P is 0. So in particular, well, in this case, so now if I coming back to this, here I have written x, coming back to this, here I have written this x at xy as a derivation in terms of the partial derivative operators. But if I think of it as a element of R2, then note that x at the point xy would just correspond to, after all, this identification here, this equality here, just involves whenever we have a derivation at p, it can be written in terms of the partial derivative operators with some coefficients, and this equality just amounts to putting the coefficients together as a coordinate vector. That we have seen that when we first talked about tangent vectors. Well, if we do that for this x, then this is the same thing as y comma minus x. And the point P is just x comma y. P is x comma y. So to see that this x belongs to the tangent space of P, all I have to do is check that the inner product of y comma minus x and x comma y is 0, like here, which is of course the case. Hence x at x comma y belongs to txy at s1, right. Now coming to the next issue is smoothness as usual. Smoothness of x as a vector field on S1. Here again it's rather than worry about the special case, let's prove a more general thing which is true for any submanifold. So here's a small proposition. Let S contained in M be a submanifold. Submanifold X a vector field on M with, suppose X has this additional property that X at a point P, if I start with a point P in the submanifold S, then X at that point should actually lie inside, be tangent to the submanifold. So TPS, which is as usual regarded as a subspace of TPM. So to begin with, X at P is for an arbitrary vector field, X at a point P, wherever the point is, it won't care. If the vector field is arbitrary, then there's no requirement that X at P should belong to TPS. But we demand this condition. Then if I restrict X to S, I get this is smooth. The proof is quite simple. It's pretty much anything involving submanifolds. It's it's easy to see any statement in terms of a slice chart. So that's what one would do here. You would just take a slice chart around P. In a slice chart, so AI are smooth. AI are the usual coordinate functions. The thing is that if AI are smooth, so AI are functions on this. So here's a submanifold S. The slice chart is taking me to essentially putting the submanifold S in RK. So this is RK and S is going to this part under a slice chart. So this AIs are functions here as I defined. Well, if AIs are smooth on this, then using this slice chart, AI are smooth, then it's easy to see that AI restricted to S are smooth as well. Actually, this does not involve anything. I mean, it's just a statement about smoothness. The earlier remark that I made, that if you have a smooth function on a smooth map on a manifold, then it is restriction to a submanifold is also smooth. That's all that I'm saying. But the slice chart condition is used because these coordinate vector fields that I get here, note that in a slice chart we can ensure that del by del x1 at q etc. del by del x and del by del x k at q are tangent to belong to the tangent space to the submanifold. So the very definition of a slice chart is that it's a chart on the full open set in M, which when restricted to S intersection that open set will give rise to a chart on S itself. So therefore we have that these things del by del x1 etc. all the way up to xk, they are all tangent to S. And since these functions AI are smooth, so actually all I care about is A1 up to AK, they are smooth. So x restricted to S will be by this condition, the fact that I have this condition, x restricted to S will be a linear combination of this del by del x1 up to del by del xk with the coefficient functions A1 up to AK. So therefore that will also be smooth. So we'll stop here, and in my next lecture I'll continue with more examples of vector fields, and I'll talk a bit about Lie groups as well. Thank you.